Okay, so we'll revise the controller design for second order plant. So consider a plant specified as 1 by point 0.1 s square. So we saw that a map from F to force to velocity would result in first order plant. Similarly, a map from force to the displacement would result in a second order plant, and similarly talk to the angular displacement. So again, similar conditions we have the controller of this form, and we have the same specification similar to the first order plant problem. Now again we start our iteration first with the constant. On substituting the values of p of s and k of s, we obtain uh, the mapping gr to y as this, but we see that this would not be biboostable for any values of c. This is because if c was positive, then the real part would be 0, and if c were to be negative, then again one of the roots would be positive, and hence the biostability would not be met for any values of c. Hence the first condition, that the nominal stability is not met, and we cannot use a constant value of k of s. Now we'll move on to the second value, the second iteration, that is of the form c s minus z1 s minus p1, similar to the previous problem. Again we substitute p of s, we substitute k of s, and we get this form. Now we see that the denominator is of cubic relation. Now we have not done any analysis for cubic relations as such, but what we can do is, so we have a good solution for second order system. So hence we try to make the cubic denominator in terms of the second order solution which we obtained, and another term that would not have a dominant effect, that is the second part, that is except from the second order system that we had solved, the other part won't have much effect. So hence what we mean is the transfer function can be uh, broken down into the partial fractions of its roots, and we see that the impulse response is expressed in this form. So if two of the roots represent combine to form the second order solution, and one of the roots has a large magnitude, that would imply that that particular root won't have much effect as compared to the other two components. Hence the dominant pole is defined as the lambda, for which the modulus is small, the modulus of real value is small. Again the biostability condition has to satisfy that the roots of the denominator, all of them have negative real part, and hence we take the modulus, and hence um, we want our denominator to look like the second order solution that we got in the previous problem times a factor for which the real part is very high as compared to the roots of this quadratic. So we see that the real part would have some value between in the order of -5, and hence we choose some magnitude which is much greater than -5. So in this case we chose -50. We'll vary this parameter in further cases. So now we have the denominator, and hence now we can also calculate the numerator, since b1 is 10c and b0 is -10c. So we equate this with this, and we get p1. So p1 is the coefficient of minus the coefficient of s square, 10c is coefficient of s, hence we have p1, we have c, and we have z. Since we have c, we get z. So we have c, we have z, and we have p1. So hence we have the we have the controller k of s, and we can plot the Bode plot and the step response. So we see that um, the 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 plots have been plotted, but we find that the dB magnitude is greater than 3.1, whereas we required the dB magnitude to be less than the m peak magnitude to be less than 3 dB. But we see that the m peak is 3.1, which is greater than 3. So now we need to change parameters such that our m peaks is reduced. So So in this case we had chosen our so the solution, that the dominant solution had zeta 0.6 and omega n equal to 8.5. And so one choice is to increase zeta, since we had seen that on increasing zeta the overshoots generally decrease. And second observation can be similar to the practice we did in first order. So b1 to reduce b1, so that is to reduce 10c, and that is to reduce this term. Now if we keep omega n to be the same, what can decrease the value of 10c is the magnitude of the non-dominant pole. So hence if we increase zeta, and uh, if we increase zeta we keep the omega n, and if we decrease the magnitude of non-dominant pole, so from -50 to we take -15, so we get the new controller and we have the plant. So we do the Bode plot and we get this result. So our overshoot has been reduced, our rise time has increased to some extent, and the bandwidth is more or less the same, and we get that the MP has reduced. So this is a good solution. So we'll discuss the other aspects in the next video.